So we're really happy to have Zack Spica join us all the way from Spain. It is midnight where he is, so thanks so much for agreeing to do this at such a late hour. And thanks everyone for joining us. So Zack, a little bit about him. He's from Belgium, and he did an undergrad in earth sciences at the Université Libre de Bruxelles. I don't know if I pronounced that at all correctly, but
yeah.
Try to give it a shot here. He visited Mexico, decided it was really beautiful, and decided to go to Mexico to do his PhD. He did his master's in Bruxelles as well. Zack just started a faculty position at the University of Michigan in January, so he had a fun time teaching his first semester as COVID started breaking out. And he got a fancy new distributed acoustic seismicity a set of equipment, a sensing equipment that he hasn't been able to use at all because of COVID. So not always possible to hit the ground running. But in spite of that, he is one of the leaders of this emerging technology, DAS, as it's called, and he's going to be talking about that today. So we're real excited. Thank you, Zack.
So yeah, I'm gonna show you some results about some old results and some new results about distributed acoustic sensing, which is a new tool in seismology that use fiber optic cables as both a sensor and also a way to transmit the data toward a receiver. And many of the work I'm going to present comes from my collaborators, Eileen Martin, Biondo Biondi, and Ariel Lelouch, that are or were at Stanford. Eileen Martin and Ariel Lelouch are not at Stanford anymore. Biondo, yes, is a professor, faculty there. Also, some of my colleagues at ERI, Earthquake Research Institute in Japan, Shinora Arasan and Nishida-san, and Jorge Castillo at Caltech. Of course, they also have collaborators, but I didn't put everyone on the list. It's not an exhaustive list, and but it's important to thank everyone because some of the results I will show are actually not for me. So because my idea is to provide you a big overview of what is this technology. So here you have a map of the commercial fiber optic cables around the world. And so these are, as I said, commercial. So these are the one that allows us to have this Zoom meeting today. It's midnight here in Spain. And we are seeing synchronously this talk through fiber optic. Probably all the information, my voice and all the data are transmitted at the speed of light over the Atlantic Ocean and go then to the continent, also through fiber optics until Utah, where you are. And so that's really a big business there. It's not an emerging, it's like a booming business there because we always use more data, we always need more communication, and these fiber optics cable are really the backbone of our modern society, our telecommunication. And just here, I show you at the bottom a cable that is installed at sea or in the ocean, just to show you how big they are and also how long they are. So they are like thousands of kilometers of fibers out there already installed. And then at some nodes here, for example, in New York City, in Miami, or many places over the US, you also have data center where all the information is transit, can transit, but is also stored, sometime for a few seconds, sometime for years. And so that's for commercial fiber, but there are also many small institutions or private company or universities that owns their own fiber optic cable as well. For example, here it's an experiment that we have led in the city of Granada in southern Spain, where you have an observatory, sky observatory, which is inside the city, like here at the north of the city. And on the top of the Sierra Nevada, here, they have a radio telescope where they observe the sky. And so they need to transmit the data in real time to the observatory. And so they have their own cable, which is about 40 kilometers long, that goes from the observatory to the top of the Sierra Nevada. And here on the left, you have what is a DAS, so Distributed Acoustic Sensor, which is, as you can see, not much bigger than a desktop computer. And it has a keyboard, a mouse, and you need also a monitor in order to see what are the parameter you are configuring. And the only thing you have to do, and that's something I was saying during the meet and greet before, I like field trip, but field trip with DAS are actually extremely boring. It's just going on the data center and plugging this instrument with this type of cable, which is a fiber optic connector, into this rack of here it's a very small data center just for the observatory. And then you put the parameters you want, and that's it. Like in an hour, your field is finished, then you have to wait the time it registered the data. So if we go back in time in late 80s, early 90s, with the advent of the global seismic network that was actually developed to monitor nuclear explosion by the CTBTO, scientists were able to pick travel time for earthquake. So here what you have is time on the y-axis, and on the x you have distance in degree. And so by just picking the P wave, here you have the P wave of many earthquakes at all these different stations, you can infer some velocities, here the P velocity of global structure at the global scale of the Earth. So that was the beginning of array seismology, but at global scale. Later on, the price of the seismometer dropped a little bit. Broad-based seismometer were more affordable, and the US led this wonderful idea of the US array that you probably know, which is a transportable array that moved from East Coast to West Coast and then finished in Alaska, of several hundred of station seismic sensors over continental US. And here it's a video from Fan-Chi Lin using cross correlation of ambient noise and this array. And so here again, you can apply some array seismology technique, so you can observe the seismic wave field with more detail than before, because you have a higher density of station. And then again, the price of the sensor dropped a little bit more, and now they can manufacture this type, what they call nodes, one component or three components, and that you can buy for a couple of hundreds of dollars, I think. And because of the price drop, it was now possible for scientists and oil and gas industry to densify a little bit more the number of sensor. And here it's again a figure from Fan-Chi Lin that I modified with a video I found on Rob Clayton on the Caltech's webpage, where you observe an earthquake wave field that cross an array of 5,200 stations in Long Beach, California. So that array was used a lot. That was one of the first like publicly available or semi-publicly available data with such a density. And I remember in 2012, many people were extremely excited by this array, and there was like at AGU one full row of poster just about research with this Long Beach array, because it was very exciting for us, like to get that level of detail of the seismic wave field and what you can get with it. And now comes the fiber seismic observation. And here it's an example with a borehole in the San Andreas Fault Observatory at depth, so the SAFOD, which is an experiment in the San Andreas Fault, where in the well they installed several instruments, and they also installed 800 meters long fiber on the vertical section of the fiber. And they connected that to a DAS, a distributed acoustic sensor, and they transformed this fiber into an array of 800 stations, so one station, one vertical station every meter. So now we can have something with, so like the density of the station can be as short as 1 meter. So, and if you apply same techniques as in the 80s, 90s, so just taking the travel time of the P wave, then you can get a velocity model very detailed. Actually, you have the P wave every meter inside your well. So the question is like, why do we want always to have more density, you know? So this is because, in fact, when you have the wave equation, there is this spatial component in it. And so you basically get a better model, or you can get a better wave field model if you record not only a simple time series, but a series of time series that vary as a function of the spatial coordinate. So you can better get higher information, better information of what is going on in the ground. And here I show you, for example, in previous slide, I just highlight the P wave. But in fact, on this graph, you can see many different things. You can see like the P wave arrival, you can see a long P wave coda, then you see an S wave, SP conversion, the S coda. And so if you would have only one or a few sensors, you would not be able to see this type of conversion. And this conversion, if you model them, they give you a lot of supplementary information, like valuable information about the structure of your borehole in that case. So this is the outline of my talk. I will first try to explain you in a few words what is DAS, what is the distributed acoustic sensing technique, and trying to demystify a little bit this technology. And then I would like to show you two different studies, one about that are kind of a frontier research in seismology, which is urban seismology, and ocean bottom seismology, which are like two different environments where it's actually complicated to acquire data. It's of course more complicated to get the data at the bottom of the ocean than in city, but sometimes in very dense city, it's very hard or complicated to install seismometer. So DAS is a laser-based sensor system that measures the change in length of the fiber optic cable. And how does it do that? Well, it sends a laser pulse or many laser pulse, and it will analyze the coherence or the diffraction, how much light is diffracted along this fiber cable, and can come back actually to the receptor. So you send the pulse over the cable, and a fraction of this pulse come back to the receptor. And if there is a change in the length of the cable because of an earthquake or because of a car that passed by, then so the length of the cable changed. So the time between these pulses will change as well. And so this, here you have like the little formula, where you have n, which is the refraction index of the fiber, the wavelength, and here is the optical defacing between the different pulses. And GL is the gauge length, which is the length over which you will integrate your measurements. So it's not a point measurement. You're not measuring the displacement, or in that case, the strain in one point. You're measuring the strain that is integrated over a spatial distances. And so this strain is, of course, proportional to the extension or the compression of the fiber between these 2 points, between the gauge length. And here again, it's the DAS interrogator, how it's look like. So it's, as I said, not bigger than a desktop computer. You need a monitor, and on the left you have a NAS, which is an array of hard drives. Because the thing with DAS is that you can record. It depends on the model of the DAS, but you can record up to 50 kilometers, or sometimes other DAS can record up to 100 kilometers of data with a sampling, spatial sampling of 1 or 2 meters. So you can have up to, let's say, 20,000 stations only with one cable. So this NAS, this array of hard drives, this one is 30 terabytes, and it fills up very quickly, because in one day you can have several terabytes of data that is generated with this type of instrument. And one thing which is important is that you are measuring the axial strain along the fiber, so the sensitivity of the wave will really depend on that. If you have a wave that is completely perpendicular to your fiber cable, then the sensitivity will be poor, because there will be very little compression or extension if your wave come perpendicularly to the fiber cable. So DAS is sensitive, or is high, most of its sensitivity is higher along the cable itself. So of course you don't have like 3 components like with traditional seismometer. You only have 1 component, and which is kind of a random component, a component along the fiber itself. And so DAS has been developed in about 10 years ago, and it has been quickly used by the oil and gas industry about 5 years ago, in order like to lower the price of, for example, lower the cost of some acquisitions for microseismic monitoring, or for repeatable 4D seismic, and many different things for reservoir monitoring. So oil and gas is now using DAS. I don't think I'm wrong if I say that all oil and gas companies are using DAS now. It's something very common. And we are seeing more and more, every day more, every month more people in geoscience that are interested in this technique. And it's only recently, maybe since 2016, 17, that earthquake scientists got involved into the DAS acquisition, and how it could be useful for our community. So I want to come back a little bit on the how does it lower the cost, because this is a question I I often have, um, and that's many people that use that says that it lowered the cost, but in fact, you have to think about several things like a DAS acquisition system. So there are many different prices. So now there are more and more companies that sell it. So there is more competition. So we are expecting the price to drop in the near future. But let's say it's between 180K to 300K. It really depends of the company. Then the price of 1 meter of fiber, it's about $1. It depends. There are also all type of price, but classic fiber that you want to install, for example, in your university, it will be less than $2 a meter. So if you take the price, if you consider that it can sample 50 kilometers of cable with a spacing of 2 meters, so you would have 25,000 sensors along your cable. So if you take the price of the interrogator plus the installation of your cable plus 50K, which would be like 50 kilometers of fiber that you divided by 25,000, then you have your price per sensor, which is really low. And you can also use commercial fiber or fiber that is already installed. And in that case, you don't need to buy the fiber and you don't need to install it. And sometimes install the fiber can be very heavy work. So I'm really interested to use already existing fiber that are normally used for telecommunication purposes. And in that case, you really, the price per sensor considerably drops. So what are the pros and cons of DAS for permanent monitoring? So as I said, the cost per receiver, it's the lower on the market. The receiver density, it's the higher that you can get so far. It's possible to have a cable in a place that are normally not accessible with other type of sensor, for example, under cities or on deep seas. On deep seas, you can install punctually some sensor, but if you wanted to install like an array of sensor, that would be extremely costly. It works. So one thing is that you just need one normal current plug, and then your DAS can work during several days. And also the fiber can work in very harsh environments from -20 degree to 80 degree at very high pressure inside wells, inside the San Andreas Fault, and it keeps working while traditional borehole seismometer, it's well known that because of the heat or because of the pressure, after a certain time, you have to replace them. On the cons are, of course, the receiver sensitivity, as I said, which is much lower than the geophone, and also which is highly directional, and also the storage. So even if you have a cost per receiver which is lower, then you have to invest into a storage in order like to store all your data, if you want to keep all your data. So let's move to urban seismology. So here I just put, it's a map of Mexico City basin with many cities actually around the world, like Los Angeles, Jakarta, or Mexico City. They are on a sedimentary, they are constructed atop of a sedimentary basin. And in case of earthquake, it may happen that this sedimentary basin produce an amplification of the waves. And in Mexico City, it's actually a very well-known phenomena since the 86 earthquake that happened like 400 kilometers away from the city and near the trench. And actually most of the damage in the country were happening in the city itself because of the amplification of this wave. So it's very important to sample with, to micro sample the city at different location in order to know or to better understand what would be the ground movement in case of an earthquake. And this not only for Mexico City, but for many cities around the world. So if we can use the fiber that was already installed, that would be best in that case. And now I want to present you some experiments that have been done in 2017 by Biondo Biondi and his team at Stanford University, so here in California. So they just installed a simple fiber in a PVC tube like that, which was about 1 or 2 meters under the ground. And they just laid the fiber inside these tubes. And they got an array here, which has a H shape of about 620 stations across Stanford campus, in a small region of Stanford campus. So at the time they asked the first question, okay, we just laid this cable there, do we record earthquake? And they were very excited to say that yes, they do record earthquake. And here you have, so this H shape, so you can have kind of 2 components. You have two linear shapes here. So you have one more or less north-south component and one more or less east-west component. And so you have here in red and yellow the east, west, and north, south component of different earthquakes from nearby faults of different magnitudes. And then they also recorded earthquake from large, like teleseism, like the Pawnee earthquake in Oklahoma, 5.8. And they were very satisfied to see 2 things. That's first, the arrival time of the phases were actually good. You can actually pick the arrival time as if it was a normal seismometer, even if it's a strain. Actually the arrival time of the strain change is pretty much the same. And they were also satisfied to see that the frequency content of the earthquake recorded with DAS was not as good as with the seismometer, but you were able to retrieve like low frequency from this teleseism. So in fact, broadband is, DAS is kind of a broadband instrument. Then the next question is, do we record ambient noise? And I'm not really an earthquake guy. I work much more with ambient noise. So this is more my thing, even though this is the work from Eileen Martin, where it's just a plot of the amplitude and the frequency amplitude of DAS recorded over several days. And so you can see this variation of day night. So, okay, we can see very small variation during the day and the night at different frequencies. But can we use DAS for ambient noise cross-correlation, which is a tool largely used in seismology to get virtual sources and compute as if it was an earthquake? You can get ballistic wave of between 2 different stations. Would it work with DAS? So here there is one thing about the sensitivity which is very different with DAS. Let's say you have 2 parallel cables and you have a series of receivers on the left and one source on the right. Well, if you do the cross correlation between all of these stations, the thing with DAS is that you won't get the same results. Here are it's color based. So if you are like purely perpendicular, you will get something. You will cross correlate the love waves, and the more you get parallel to the cable, the more Rayleigh wave contribution you will have in your cross correlation. So that means that if you want to get Rayleigh wave, love waves, you really need to have perpendicular cables. And if you want to get love waves, you need to do Rayleigh waves, you need to do cross correlation along the same axis of your cable. And here, if you are in between, you will have a combination of the two, of love waves and Rayleigh waves. So that's what we did at Stanford University. So we took a linear section of the cable and we compute Rayleigh waves for which we are able to retrieve dispersion curves. So using the velocity of these Rayleigh waves in the frequency domain. So we can then, I will show you that later, we can use this information because that gives you an information of the ground and the velocity of the waves in the ground, so you can invert this velocity to get more information and get the structure of the ground. And if you look in time, so this was September, November, and December, we see that there are some changes into these cross correlation, and here January. So, which means that you could also use cross correlation that change over time. You can use that for monitor the city or monitor the campus based on here it's every time you have a shot getter for every month. And actually that was there was a very nice work from Fang and others at Stanford University where they are able to retrieve very small variation in the structure of the campus over several months due to the construction of a building on the campus. So if it's change over months, we need to only focus on the section. If we want to retrieve the structure, we need to focus on a section of the dispersion curve that is stable. So we stack them over time, over 1 year, and we are only taking here the section of the dispersion curve that has low dispersion or low, the variation of the velocity is stable over the year, while at a higher frequency, you see that these beams are much higher and you lose coherency. And so measurements are not good in that section of the frequency time diagram. So now if we move along our array, so we are here with the little yellow dot, which is the virtual source. And on the left, you have the dispersion curve. And we can see that we can retrieve some spatial variation of the dispersion curve across our array. So that's good. It means, in a sense, that it works. We can retrieve very short scale variation of the structure of the Rayleigh wave, how the Rayleigh wave propagates at a scale here. It's about, I think it's every 50 meters here. And then we tried with another linear array, another section, another linear section, but it didn't work. And that's because a noise distribution matters. Here on the top, you have run I forgot the name of this road, but there is it's one of the most used road inside the campus. So that was a regular noise source that was actually perpendicular to our, parallel to our array. And in the other case, it's perpendicular. So it failed to retrieve cross correlation if you are not well aligned with the ambient noise source. So then I asked myself, what else could we get from this data? We can get dispersion curve. That's already a good information, but can we get something else? And I found this paper from Chun Kwan who was a postdoc at Caltech at the time. And what he did, he combined DAS data from the Goldstone experiment with seismometers, with the vertical component of a seismometer, and he computed receiver function by combining both DAS and seismometers. And he used this conversion factor that the strain can be transformed into displacement if you have an idea of the velocity structure, of the phase velocity under your array. And he showed that it was working fairly well, and he was able to retrieve a receiver function, like trustable receiver function for the region. So I thought about this kind of the same process for H/V spectral ratio, which is something I work a lot during my PhD. And spectral ratio give you the frequency of resonance of a site. So what you do, you take the horizontal over the vertical component of a 3-component seismometer, and with a little bit of processing, you can retrieve these H/V curve that give you the frequency of resonance of the site. So in that case, again, it's Mexico City, and you see that how the waveform are amplified, and you can get an idea of which frequency are actually amplified thanks to this type of measurement. And following Chen Quen ID, I did the same with DAS and seismometers that were installed on campus. So I took the vertical component of the seismometer and I compute different H/V across this linear sub-array of our DAS array. And here you have like in gray, the broadband station that was installed in this building here, and other other H/V ratio that were computed with DAS and combination of the vertical component of this station. So now we have both dispersion curves and H/V that we can combine for joint inversion in order to retrieve like the shallow velocity structure on campus. And we did that at several places on campus, unfortunately only for this section of the array, because as I said, noise distribution matters. And in that case, we were able to get a velocity model of the shallow surface every 50 meters across the array, which is probably, so here on the top of the right, you have a survey that was led by a private company in Stanford University in order to get site-specific seismic hazard, but we get a density and a resolution probably 100 times higher than this company using the fiber optic they installed on campus. So I have to hurry up a little bit. Now I'd like to switch to ocean bottom observation, which is also like kind of frontier, because I think that in earth science, that must be one of the most expensive experiment. Every time you want to install one seismometer at the bottom of the ocean, you need a ship, you need a crew, you need a lot of scientists involved, and just one seismometer at the bottom of the ocean can be extremely expensive. And there are many cables, as we have seen in like one of the first slides of this presentation. There are many ocean cables that are already existing and lying at the bottom of the ocean. So what if we use these cables? And in Japan, they have a lot of cables that are actually cabled seismometers, cabled ocean bottom seismometers, such as SNET, and they all connect to the landing station through a fiber optic cable. So it's possible to use one of these cables and connect it to a DAS, and we connect it to another type of DAS here, and we got an array for the first 100 kilometers of this cable. We got an array of 19,000 channels or 90,000 horizontal stations, all spaced by 5 meters. So that's a lot of data, and we got that for maybe they record data for 2 days, and then they change the DAS and they record it for 2 weeks. And of course, in Japan, there are a lot of earthquakes. And here I just show you like an earthquake that happened in this region. I couldn't tell you exactly which one it is. It's just a small magnitude earthquake. Well, not that big, 3.7. And you see that the P wave, because in Japan, the subduction is very steep. So the earthquake, they arrive almost vertically, or they're very steep angle to the station. So the P wave is very hard to observe on this data. But the S wave, which is a shear component along the fiber, this you can observe it very well. And I was kind of surprised by the length of this coda as well. Why is it shaking so much? Like after the earthquake passed, even if it's a low magnitude earthquake, well, as I said, I'm not really an earthquake guy, but for me, it was kind of long coda. And I come back to that in a minute. But I think the most incredible thing with ocean bottom DAS is the diversity of signal that you can record. You can not only record from the bottom, like earthquakes that come from the trench, you can record also the things that happen in the ocean, like in the 3D volume. You can record if there are like ships at the surface of the water, because you can hear the engines. You can, I haven't seen that yet, but I'm pretty sure that you can retrieve the waveform of whales singing, for example. And another thing that you can observe is just the wave, the oceanic gravitational waves that traveling at the surface of the ocean. So these are literally the little waves that are traveling at the surface of the ocean. And we know that because they have been theoretically observed, theoretically described. And so we can, thanks to this equation, we can, and the depth of the height of the waves and the depth of the cable, we can retrieve the frequency of this. Well, we can observe, we know the frequency at which it's going to be excited. And here on this video, it's actually a frequency a frequency wave number diagram where you see, so it's a section of the, so here, every time I take 600 stations along the cable and I move from the coast toward deeper depths. So you see here the red dot, it's going to go from the coast back, and then it moves to at depth. And you see that near the coast, you have these two, let's say, horns, like these two shapes, like V shape here. Well, these are, if you plot this equation on top of this graph, these are literally the oceanic gravitational waves. And when these waves enter in, they have like complicated nonlinear process, and so they enter in resonance with themselves, and they propagate a pressure wave that hit the ocean bottom, and so that creates some surface waves. So that's the origin actually of the secondary microseism. These are the waves at the surface that start entering an interaction with another, and so that generates some shortly waves at the bottom of the ocean. And so these are surface waves at the interface between water and the ground. And so you can see that there is some dispersions in these waves. So these are really surface waves that you can extract, and as well as at Stanford University, you can extract them and invert them to get the velocity structure at the very fine scale for the shear waves, in that case, at the bottom of the ocean. Then one very last thing I'd like to show you is some, we are looking into, so to come back to the coda, I told you there is a very long coda of these earthquakes. So we were trying to understand what are these codas. So we were doing some full wave field simulation of these waves using a setup similar to the DAS cable in Japan. So 19,000 stations along an array along the coast of Japan. And here is for an earthquake 5.5 that happened more or less under the array. And what I want to show you here is not this wave traveling here. It's really, you see that there are a wave that goes up and goes down, goes up, goes down, and it keeps going up and down for a long time, even after these other waves pass away. So here it's continue, and it gives a lot of energy. So it's still continuing. It provides a lot of energy to the ground that propagate along the trench. And we think that these waves may be at the origin of this long coda, and they are probably like surface waves that propagate after, that are generated because of this phenomena of wave bouncing up and down from the bottom to the surface of the ocean. So if we look at the record section along the array, I'm not sure you can see it on Zoom, but it's very hard to observe this surface wave with low velocity here. So we did apply some curvature filtering in order to filter out all the waves that have not the velocity that we want to observe. And now we are more able to observe these surface wave with a low velocity, and that might correspond to these wave that creates long codas on these records. But this is work in progress, and now my next step is to look into the real records of DAS and see if we apply the same type of processing, if we can retrieve this similar type of waves. And as a last message, I'd like to say that there is clearly some advance in sensor technology, and that we are making better seismic acquisition. It's easier, but we have we have higher spatial resolution, cheaper continuous recording, and we can do that at the ocean, the bottom of the ocean, or in urban environments more easily. But it comes at the price of that we need to develop new numerical and mathematical advances. We need to, because we will face in the future new problem that comes out because we need to scale up our algorithms. We need to optimize the data storage, optimize the analysis, because the quantity of data that we are generating with DAS is actually exploding, and it's, yeah, there is a lot of work that needs to be done numerically and mathematically to face these challenges with DAS. So now I will take your question, and thank you for your attention.